preview of everything we'll be doing. Here we go. We want to install TensorFlow. If you've seen the news anything recently, this is a library that Google came out with a couple months ago. What they use to do neural networks and applications. So we'll get into one of these later. The first thing you need to do is actually download it. So on your whatever your local computer is, you should go to this URL, or you can just search TensorFlow, and you can find it very quickly. Sure. If you're running on Linux, you have to get URL or search bar and find it.
The URL doesn't move on to the next one.
Yeah. I wanted the text to be big enough and I had to plot between this. So this is stored at Google / TensorFlow. This is the CPU version. They have a GPU enabled version too. That just means we run on your graphics card for designing a local processor. But since we're using the free Sage Math Cloud instance, we have no graphics card, so we're just going to use the local version. This is the version for Python 3, and it's going to be compiled for Linux with Sage Math runs underneath. Really, you don't have to think about all that. That's just, it's nice to know. And once you have downloaded this file, you need to go into your Sage Math Cloud instance and say, hey, create or upload a new file, and you upload that file. It's not being super long.
Page building about two.
Is that
Can I cross that page so I copy URL?
yeah, if you go to the GitHub link I gave, you'll be able to go to that and it loads up. Click on it, open it up. And it should run here, yeah. Cool. And then you can go down to the bottom part.
I'm sorry, am I doing this
On your local computer, you're downloading the file. Okay. Sage Math Cloud, for security reasons, they don't let you call out the network directly from it. Because when it first came out, someone used it to launch botnet attacks. So you have to do this run around, but you download the file locally and then you upload it directly.
So,
Okay, you don't have to, so I guess you don't have to look at it, that's fine. So you can just put that address into a browser. So just copy and paste it. Yeah. It just would have been the power on, right? It's possible. It's like
I'm not sure whether or not it's that's it. So supply power, supply check to make sure it works, right?
And once that downloads, you'll go to create new file,
Comment.
and you upload that. And then, in our Sage Math Cloud, okay. That'll keep me grounded. In our Sage Math Cloud, we have to actually install it now, just to get the file. So you want to open a new terminal in there. So you create new, and you go to terminal. Down in the middle. And so this is an actual Linux terminal in your Sage Math Cloud. And you just want to run exactly that line. So pip3 is Python's packager. So it install things for us. Install says to install. The -- user is because you don't have admin access on the Sage Math Cloud instance. No index says, don't go bother looking on the internet for this because you can't see the internet. No dependencies is because Sage Math Cloud thinks things aren't installed, they are. And then just the world politics. And you can't just start typing tensor int tab, and it will tab quick for you. And again, this pip3, this is on save math file, not on your local.
Provide a black and this is black.
Alright, you need this to the terminal still.
Yeah, so
Yep, the terminal. Then you run this 50 commands to actually install it. It should say stop, and then it should say clean up. It's on. And we just have one more thing to install after this. TensorFlow is a very useful library for building neural nets. Let me go up a little bit so you can still type that. But there's a little bit of a ramp up for learning how to use it. Thankfully, Google has come out with this thing called skflow that's a higher level wrapper. So it'll let you, in one line, specify a neural net. Now, you can't, it's not as general. It's sort of built with certain models in mind, but for learning, it's very, very useful. All right, so everybody's got TensorFlow installed, or they think they have it installed. That's perfect. So next, we're going to install skflow. This works the exact same way, essentially. You just need to install, in this case, they have posted it on GitHub. You can just install, download this zip file. You don't need to.
I'll send the lights up.
Let's try it. How does that work, people? Too dark? Oh, wait. And there's people in the shop, so. Alright. We'll try it. Sorry, so you can download that file on your local computer. Pick up TensorFlow, skflow, and
Everything them off, you got right away.
upload the file so you can log in, run one more install, and then we'll be done installing. So we won't need to install anything else.
Dan, if you need the lights off, your presentation has ready.
I don't think so. I did the lights.
I understand that. This presentation still has right of way. That's all I said.
We'll just use your remote lights.
And some batteries work, some don't. Neither one's.
Alright, when everyone has gotten the skflow installed. Alright, good. Look for somebody, so I'm going to go help us. What's it say? So, okay, it might be called skflow master. Yeah. Let me update that. Just basically have a separate room. Yeah. So yeah, it might have a different name. There we go. So if it wasn't called master, it will be called skflow-master. Just the nature of the beast. And once everyone has installed that, scroll all the way to the beginning, and we will get started properly. Hey, you here for the workshop?
For the beta? Yeah.
Yes, that's it.
Okay.
If you have a computer, you can start going. If you don't, that's fine. You can just watch up on the live screen there. And you can take a seat anywhere. All right, so we no longer need, everybody has this information. I'll leave that there for now. All right, so now everybody needs to make a new IPython notebook. See, Jupyter notebook installed in your Sage Matplotlib instance. This is sort of be a core tool we're going to use. Jupyter Notebook through Sage Notebook. It's basically a really nice way to use Python interactively and also embed images and formatted text and switch to R, a different language, or Julia, yet another language, or Python 3 and then Python 2. It's very nice to say. It's a workflow I really like to do.
Other languages also R and
Yes.
the 30, 40 languages, right?
There's a bunch, and it's very, very general, the things that people have added to it. Any kind of interactive interpreter can probably be coerced into working in a Jupyter Notebook. All right, so if you've got a Jupyter Notebook open, then you can properly get started. So this class sort of assumes you have some understanding of Python, but even if you don't, you're probably going to get a lot out of this. If you're doing any kind of machine learning or data visualization or something like that, you're probably going to be doing a lot of number crunching, and that's where you're going to be using this library called NumPy. This already comes in Sage Math Cloud, so you don't have to install anything new, so don't worry about that. But in Python, you have what are traditional lists, which is just sort of an arbitrary sequence of objects. So you might have L is some... yes, we'll get to that. Let's do that right now. We're going to be using Python 3, so where it says kernel in sort of the upper center, you go kernel, change kernel, Python 3. So we're trying to be modern here. Python 2 is an older version of Python that a lot of people still use. When TensorFlow first came out, it was only Python 2, and this made a lot of people very upset. But they've fixed that now. Where was I? We're talking about so we're talking about NumPy in regular Python. So in regular Python, you have lists, and they're just arbitrary sequences of things like integers, 3, strings, ABC, or Python functions, math.sign, or anything, any kind of object in Python. And that's great because that's really general. You can do whatever you need to do. You don't have to think about it. But it's also a problem because it's really slow and really inefficient. Because if you have a lot of things, you say, oh, I want to access the 10,000th item. Well, if it's just an arbitrary collection of items, you sort of have to ask each item, hey, where's the next thing? Hey, where's the next thing? If you just had one block of memory and every block was the same size, you could just say, oh, well, I know it's 10,000 times 4 to get to the 10,000th entry. This is how memory works, sort of. I'm cheating a little bit. In lower level languages like C or Fortran, they're just blobs of memory. Python lets you do that in a way with this package called NumPy. And in NumPy, instead of using lists, you're going to try to use arrays for everything. And arrays are really just blobs of memory, and you're telling NumPy, say, hey, just pretend they're integers and give me enough space for that. So the first thing you need to do is, in your first cell, just import NumPy as NP. I always do that because I hate typing NumPy over and over. So in Python, this means that we're going to say np dot to access whatever's in the NumPy module. And if you want to run a cell in Sage Math Cloud, while your cursor is in there, you can hit Control-Enter or Shift-Enter, and that will run the cell. So we'll actually run those commands. Or you can use the little button up here as well. So arrays are kind of nice, and NumPy has a lot of built-in things to make an array. You can, for example, say, give me an array of all zeros that's 10 long. Let's split this, shall we? Cell split. Is that a thing we can do? I could have sworn we could split cells. Split cell, there we go. So I'm just going to make a new array of 10 zeros and print it out. And what should happen is it should print 10 zeros. This might look superficially like a Python list, but it's different behind the scenes. Zeros are good. Do you also have ones? Ones are, if you have ones and zeros, you have everything you need. So let's try that. You can do numpy.ones in arbitrary size, say 20. That's nice. So right now we're just playing. We're getting used to what's going on here. If you can get used to numerical computing, then you'll be fine with NumPy. All right, what else can you do? Well, you can, given a Python list, you can convert it into an array if everything is the same type of object. If everything is an integer, if everything is like a Boolean value, true or false. And I think even if everything is a string, it has some means of doing that, which is a little bit like sorcery to me. So you can do that. NumPy also comes with a random number generator. So you can say numpy.random, and you can say, hey, give me a random integer, randint, between 0 and 1. And in this case, I'm saying, hey, give me a 2x2 matrix of random things. Let's print out both of these. Or let's print out one of them, I guess. Oh, no, 1, 2, 3, 4. So 1, 2, 3, 4 becomes 1, 2, 3, 4 down here. And my random matrix of random.randint, again, the 2 says how many things are we talking about. If we said, I think, 1, 3, then it would give me things that are either 1 or 2. Yeah, 1s and 2s. And if you want to know, well, how many rows do you have? You can change that first number. And now I've got 3 rows here and still 2 columns.
So when you say 1, 2, 3, it doesn't include 3? That's what
No, it's non-inclusive. That's typically how Python works, and we're going to get into that in just a second as well. So has everyone at least like been able to import NumPy and make some arrays? And you can play around with whatever you want in your notebook. If you screw up, there is an undo in the notebook. I believe you can go in the history. You can go back I think as far as you want, maybe not as far as you want. You can just keep clicking until you get back where you want. So that's a nice feature. All right, so suppose you have an array. What the heck are you going to do with it? Well, often you don't actually want the whole array. You build up a whole array at once, and you just want to look at part of it at a time. So in Python, you can do this with lists as well. You can take what's called a slice of an object. You can, let me split this again. So here's a list that we're making, the numbers from 0 through 19. This is called a Python list comprehension. We're actually not going to use it that much, but for the purposes of this, we're going to try out. And in Python, you can say, hey, give me that list A, but start at the 5th element, and colon, that means up to, and if you say nothing, it means go to the end. So we're skipping the first 5 elements here. And you can see it starts at 5, 6, 7, yada, yada, through 19. So you can do this with a lot of different things. You can say, hey, go up to the 10th element. So this will be 0 through 9. Again, it's the not inclusive. 0 through 9. You can also say negative something at the end, which seems really strange. That just means stop that many from the end. So if I say -2, it's going to say, all right, I'll stop at 17. Because the last one is 19. If I said stop 1 back, that'd be 18. Stopping 2 back should be 17. And we'll see if I'm lying. OK, stopped at 17. Excellent. This is just to get you comfortable with manipulating arrays, doing silly things with them. One other really cool thing you can do is given an array, so you can take the start value is before the first colon, the end value is sort of at the second colon, and if you have another colon, that's sort of the skip value. So here we're going to take every other element starting with the first one. So in this case, all the evens. If I wanted all the odds, I would start at the first element number 1. You index from 0. So index 0 is the first element. Index 1 is the second element. And now I have all the odds. If I wanted every 3 guys, so if you a person who uses 3 vins and throds, you can do that too. And if you said, well, give me all of them up to the 10th guy, whatever that is, you can do that. So that's another nice thing just for fiddling around, getting what you need. And this is all included with regular Python lists, and also they come with NumPy arrays. But let's start looking more at our arrays. So NumPy has a nice feature called arange, and this will give us an array that is basically 0 through n, in this case 99, since this is 100. And what we're going to do is we're going to take that array, and we'll do reshape, which says take that one-dimensional array that's 100 elements long and make it into a 10 by 10 block.
So let's do that, and then we're also going to access a single element of it. So this B of square bracket 1 comma 2 says, give me whatever value is in the first row, or is in row 1, column 2. So let's do that. So A range gives you the numbers 0 through 99 here, and we've reshaped it to be a 10 by 10. And so conveniently, like we've got all the, we're going up by 10 in every column here. Kind of nice. And what's in position 1 comma 2? Conveniently enough, in this case, it's 12. So that's easy to remember. Okay, that's how you access a single element. What if you wanted to access, say, an entire row or an entire column or something like that? Let's do that. Let's take a look at that. So you can say, give me the first row, row 0, and in NumPy you can say, use this colon and get all of the columns. So that's essentially this row and all the columns. So it should be an entire row. What did I do? There we go. So we've got 0 through 9, which if you recall up here, is the first row and all the columns. And what if, just for giggles, since we're playing along, what if you wanted the first row and every other guy in that, every other column? You can do that too. You can get the evens, you can get the odds. You can play that kind of game. Let's look at some of these other things. You can grab all the rows in just the first column. It doesn't care. If you want to access only certain elements, this second one is kind of unintuitive, so we're going to explain this. What this is going to do, this is going to say, give me row 1, column 6, then row 2, column 7, then row 3, column 8, and then row 4, column 9. I'm pretty sure that's what it does. So this first line was just this first thing here, the first column. And then we got, okay, what's row 1, column 6? Well, that's 16 in our array. And then 27. And then 38. And then 49.
It doesn't make any shape.
Huh?
It doesn't make any original shape.
No. In this case, you're pulling out, you're going to end up with a one-dimensional array. And that's the nature of how you grab this. So it kind of like automatically zips it up for you. You might think, well, I really want all of rows 1 through 4 and all of columns 6 through 9, but that's not what this particular thing does. But that's okay.
You can always put it back from
Yeah.
the input. You can always put it back in a matrix.
Yeah, we haven't manipulated B at all, so you still have B itself. All right, what else? What if you say, I want to know what elements of my array happen to be odd? I believe use truth values to pull out certain elements into a new array. So this B %2, that says, is this even or odd? And if it's 0, that means it's even. If it's 1, that means it's odd. So here we're saying, give me all the indices to my array that are odd. Really, it's going to give you a new array that's a bunch of trues and falses, and that's how it's going to pull out what it needs to pull out. And so you see, these are all the numbers from 1 to 100, 1 to 99, that are odd. And we could say, well, do 0 instead. And those are all the evens.
Are those the values from the original array? Or those?
Those are values in the array B.
Okay.
We haven't done anything to change this array yet. This is still the original array we did here. Every time you're accessing an element, or even when you're reshaping, you're not changing the original array. It's only when you save it off. Now, if we said that, for sake of argument, B of 0, 0, so the very first row, very first column, equals 100, and then we print B, let's comment this line out. Now you've changed the original array. So if you assign a single index, you can put a new number in there. Now you've changed that array. Okay, so that's the basics of arrays, which are just blocks of memory that you can access in interesting ways. Now, if you went to high school or college sometime in the last 100 years, you probably took a class or had some work on linear algebra, and maybe you liked it, maybe you hated it. Doesn't matter. In NumPy, it can do it for you. And it'll yell at you if you try to do it wrong, usually. So if you have an array in NumPy, you can pretend it's a matrix like anything else. Let's take a look at that. And we're not going to go over what matrix multiplication is here. You just might remember that it's not regular element-wise multiplication. However, if you try to do B times C, B is just some 2 by 2 thing, C is some 2 by 2 thing. They're all numbers 0 through 9. If you want to do just each element, so each 3 times 6 is 18, each guy in the same position multiplied with each other, you can do that. So this isn't really linear algebra, this is just convenient multiplication. However, to do actual linear algebra, you can do matrix multiplication with the dot operator. I really hate that it's called dot, because that has a special meaning in linear algebra. They should have just called it matrix multiply, but that is what it is. So let's take a split there real quick. And you can see this is a very different result from just multiplying each element of each matrix. And we didn't have to think about that. We didn't have to implement the actual operations. It knows what to do, and more importantly, it's a very fast operation in NumPy. NumPy is actually coded at the low level, I think in C or Fortran, and so Python is just calling these fast libraries. And because you've stored your data in an array, it can do that. Whereas if it was in raw Python, then it's slow to do. So NumPy helps get around a lot of the slowness of Python. Other common things you're going to do in linear algebra, you're going to transpose an array. That means you're sort of going to swap which things are the rows and which things are the columns. So you can think, it's not exactly like rotating your matrix, but you can think of it like that if that helps you. And also, if you need the inverse of your matrix, which is another common operation, or the pseudo-inverse, whichever you need to do, you can do that as well. And that's just numpy.linalg.p inverse for pseudo. And you can do the computations there. That's nice. So B, again, was 3936. So B transpose is, of course, 3396. So all we really did was we sort of flipped along the diagonal, you can think of it as doing. All right, that's cool. We haven't actually looked at anything yet. We've only seen numbers. I like pretty pictures. So let's do some of that. So matplotlib is one of the more, we'll say, mature plotting libraries available for Python. It tries very much to be like MATLAB, if you're familiar with that piece of software, which does pretty good plotting. And it's very well integrated into Sage Math Cloud. If you do this import line, which is import matplotlib.pyplot, and as PLT is, that's the standard way people like to import it. So if you're ever like reading a tutorial online, which I highly recommend, you'll often see them import it as PLT. And then we're going to call this %matplotlib inline. This is sort of IPython magic, which is like what the this notebook is running in. That will say, hey, when you actually plot an image, plot it right below our code so we can really see it, and don't just keep it as a Python object. A couple other things. We're going to do this, change a couple parameters, this plot.rc params, make that 20,8. That just makes our images bigger, so they'll fill up the whole screen. By default, they're only like yay big, which when you're on your desktop at home is fine. But when you're on a notebook like this, you maybe want a little bigger. And also, we're going to say plot.style.use ggplot. This will make your images look so much prettier. The default style is this very harsh, it feels like 1992 or 1987. It's like a bright blue and a bright white. It's awful. This is a little softer, more pastel colors. Your data won't feel nearly as intimidating if you use ggplot. So that's just getting things set up. And note, matplotlib comes for free. It's already installed in Sage Math Cloud. All right, so you can. Does everybody have their matplotlib imported? Should yell at you, but there's an entire possibility that it might. You don't have to run every line in its own cell. You can put multiple lines in a single cell.
If you just hit enter, it should go to the next line in that cell. Are there any questions so far? Am I going too fast, going too slow?
He's using the same instance of Jupyter.
Everyone is logged into their own account on Sage Math Cloud. You can make a free account. It connects you to the Amazon cloud.
Sage Math Cloud?
Sage Math, cloud.sagemath.org. I don't know if it works on phones. I haven't tried. I wouldn't be surprised if it did, but I wouldn't want to try it that way. Okay.
We run this, we should get something so we get it like.
No, this is just setting up parameters.
So it does nothing.
Yeah, it does. Well, it does things behind the scenes.
Yeah, yeah.
It's not happening.
Right.
There's no output yet. No, the satisfying is coming soon. I promise. So let's make some random data and look at it. And what I have here, this just says, give me random numbers, 50 of them, 0 through 9, and then I'm going to add that element-wise to the numbers 0 through 49. And so what does that look like? It looks something like this. Yours might look different because you might have a different random seed, and that's fine. But we're taking we're starting with numbers 0 through 49, and then we're perturbing each one a little bit. So overall, these numbers are going to be increasing the further into our array we're getting, but not exactly, not just straight up. And then the command to plot, if you just have a one-dimensional thing, and you just want to say, hey, these are my y values, and just treat the index as my x values. So plot this in the first position, plot this in the next position, so on and so forth. You do this plt.plot. Let's try that. Let's actually take a look at what it's going to be, and then I'll run it in case it takes forever. Sometimes Sage Math Cloud gets hung up. So you can see that this is kind of bouncing around, generally going up. Here we've got really tiny axis labels, down here. Let's see if I run this, how long it takes. Yeah. And if you didn't do that %matplotlib inline, you would just see something like this. It would just say, yep, I made an object that I did the plot, sure. But you wouldn't get to see it. And you would say, that's dumb, I want to see something nice. All right, so that was something. This probably covers half of the situations I'm in when I'm plotting data. I just want to see, what are these numbers doing? What do they look like? And then I can see, oh, they're pretty much going up. And then I can move on to whatever my next step is. But if I just looked at this, if all you did was print the array, you'd say, well, they're kind of small here, and then they're mostly 2 digits. And you'd have to look real close to say, oh, well, it's increasing a little bit each time. Interesting. All right, so that's plotting one-dimensional things. What if you have some x data and you have some y data? So you've got a scatter plot. Let's do something like that. So here, I'm saying give me an array of random numbers, 0 through 99, and I want 30 rows and 2 columns in that array. And what essentially I'm doing here is I'm saying I want my x's to be all the rows in the first column, and I want my y's to be whatever that second column is. Yeah, that's good. And then I'm going to do this 2 more times. And we're going to plot all 3 of these data sets, this x1, y1, x2, y2, x3, y3, on one plot. We're going to give them all their own colors. And so the way you do that, you can say plot.scatter. It says, well, what are your x's, x1? What are your y's? OK, those are there. And then you can say color. And there's a million different options in matplotlib. But it has a lot of built-in colors. R stands for red, G stands for green, B stands for blue. You can look up other ones on the matplotlib homepage at your leisure. This alpha value says, how transparent is this data point that we're going to plot? So we're going to set 0.6. If it was 1, I believe that means it's opaque. I might be mixing that up. And 0 would be essentially invisible. So often you just want to plot things totally opaque and just see what it is. S, this is the size. how big are we going to plot this each data point? Normally, I don't fiddle with that, but for the purposes of this, I did, so you can actually see it. So note, I've got the red ones here, they're red in the size of 1,000. We've got green ones that are size 2,000, and we've got blue ones that are size 4,000. And let's run that. Oh, I didn't like that. Let's see, what is it? Self.edge colors, something. Did I not run something? So this is always the danger of doing a live demonstration. Tell you what, let's plot one thing at a time and then see where I went wrong. Doesn't like that at all. That's weird. Self-returning scalar instead, but in the future will perform element-wise comparison. Interesting. All right, now we get to try to debug in the middle of a talk. Yeah, it should be a lowercase s. Let's see. Let me just print x1, y1. Let's see what happens. This is another thing that'll happen a lot when you're using Python to do anything. It'll break, and you won't understand why. Yours works. Excellent. Oh, it was a warning. Interesting. Did mine secretly work and I was too impatient? It might be the case. Let me try that then. That. Oh no. Let's see what it says. Oh yeah, it worked. It came up with a warning. What does this actually mean? Element-wise comparison failed. Returning scalar instead. All right. We're not going to worry about that right now. You should get a picture that looks something like this after it yells you. In the opacity, the alpha value is kind of hard to tell on the projector, but you can see like where this green overlaps this one, it's a little bit darker. Where this green happens to overlap the red. So in this case, you can sort of see, oh, there's an interesting. In this case, you can see there's no patterns at all, I guess I should say. But you can plot your different data sets on the same graph, and you might see, oh, these things all tend to be over here that are blue. These ones are all red over here. Maybe there's something different going on. All right, so that's plotting scatter plots. Has everyone gotten to the point where they have a pretty looking picture like this? Yeah, let me leave that right there. You also not change the size. Yeah. So typically, you'll change the size if you're showing like the population of cities on a map or something. So each city is going to have its size. That's common usage for that. Here, we're just sort of using size to better differentiate between different plots. So in that case, you're going to be plotting sort of doing individual calls. All right, what is next? Are you following along, sir? Okay. Did you go to cloud.sagemath.org? Okay, you can do that and run everything there. You don't have to install Jupyter yourself. And there's a rave going on. Okay. All right. This is Python 3? Yes. So if you change your kernel, I don't know which one you're in. Oh yeah, you're right in there. You're running your own version of Okay, so you have matplotlib on here? Let's see. Yep, you got pandas right here. All right. Has everybody made a pretty picture that they like? Or a pretty picture that they hate?
So, figure out. Most of those.
Okay, yeah, I definitely thought it was right. And I realized I'm not typing code up here. And that's the major difference. Right? Okay. So where are you?
He's just.
Okay, that's fine. And you can go to the GitHub page that has all of this. Yes.
Violating the two
If you want to do that, I can say it. This is the first time I've given this lecture to you guys are using any of this. So GitHub.com/db12. Yeah. And then db12. Giving all the all my initial slides to create the repositories and all of them. And just click on that and it'll workshop that I and then GitHub will render my Python notebooks. It's super great. I don't recommend putting notebooks themselves under Git version control because they're sort of binary. I fiddle around with using text formats for them, and that's okay, it's not great. And so you have that, then you can just look at it, or you can copy paste whatever you want to do.
There's another one.
Oh, I haven't tried this. It's realized now. Oh, no, no, no.
I started this one back on here.
Yeah.
Let's do some measures.
All right, you can always reload the notebook. I believe that essentially that turns off my Python, turns it back on. You'll have to rerun some of the cells, and it saves like your whole printout. All right.
And we are just going to check out one more, I think, super cool plot. So I was saying that heap plots are the coolest things. So if you've got a whole bunch of data points, and they all occur at specific points somewhere in your space, like maybe you're looking at, I don't know, what's the fire hazard in this quadrant of the city, say? A heap plot is often a great way to visualize that, I've found. And so what this is we made a random array here, as always, the numbers 0 through 9, and I said, make it 20 by 20. And when you do .pcolor, that just says, hey, give me a heap plot of all this stuff. So each color here is tied to a particular value in the array. And you can plot a legend to get that specific value, but if I'm doing this, I often just want to see, is there something obvious going on here that if I were just looking at the numbers wouldn't be clear at all? In this case, there's not, because I just made random numbers, and Python's random number generator is pretty good. But you can say, well, don't give me 10 things, give me 2 things instead. And you notice you get 2 different colors. Here it's like this red and this blue, and we get this annoying warning. About 100 things. Well, then we see pretty much the same what we saw before. So I believe it spans, by default, excuse me, this dark blue is going to be the smallest value, and this bright red is the biggest value. And so you can make a random array of whatever size, or it doesn't even have to be random. Make some array, and then just do plot.pcolor. And then you can sort of get this overall sense. If you have a lot of different values, and each one and they're in a large matrix, and they can span, say, 0 to 10,000 in value, this might not be great just for looking at it, because 9,999 will look a whole lot like 10,000. Or rather, like 100 looks a lot like 101. They'll both be yellow and then like yellow tinged green. So perfect for Crayola, making all their different colors. Not so good for you trying to see obvious differences. Let's just see what pretty pictures that people made. How big of an array. You got this right to me. We use the center of this. Yep. Or you can pretend like you're playing an old card game. Nice display graphics.
Beautiful. All right, let's keep going with this. There's no reason to leave it. Right now.
Yeah.
You don't have to do 4 every time. It's like running one time every time. I mean, if you want to do that, just so you can like copy any given section. Okay. Yes. You want a range, and you have to make it 100. That's saying how many. A range makes a one-dimensional array, and then you do that reshape. And your ending shape has to be the appropriate size.
There's a class going on.
How's it going? I'm Dan. Zil. Sinar and Zil? Zil. Sino and Zil. Cool. Are you guys here for the class? Are you here for open hack night? Open hack night. Okay, cool. Fantastic. Data visualization and machine learning. Yeah, I mean, feel free. I'm going to be yakking the whole time. We're about halfway through, so don't worry about it. All right. So if everyone has made their super cool heat plot, what's the most simple heat plot you can do? Plotting zeros and ones. And I don't know if you've ever stared at your television or an old school television. This might look like a very familiar screen. So I'm going to hide the code for just a second. And you tell me if you can find the sailboat. If you magic eye it just right, you won't see anything. These are just random numbers, zeros and ones, that are, I made 128 rows and 512. Those are powers of 2. I'm a fan of those. And to get black and white, you use this plot.cm.binary. This says, hey, in the plot module, use the color map of binary, zeros and ones. And you say, hey, the C map needs to equal this. And I called it sailboat just for silliness. But this is still the same P color that we were using before. And I tell everybody, look for the sailboat, because humans are really, really good at pattern finding. We're so good that we'll find patterns that aren't fair. So it's another thing to be careful of. Like in this particular image, you might say, oh, there's like a streak of white right here. Is that something? Or like there's a lot of black going on right here. But you can make yourself see whatever you want to see, I've found. If I want to find a face, I can easily find a face. Like here's a wolf's head, definitely. There's an ear. There's another ear. There's a snout. For sure. Let me see if I run that and I get something new. Takes a little bit of time.
Many Pac-Man characters.
Yeah. But that's just another example of things that you might want to plot if you've got a whole bunch of zeros and ones. Yeah, this totally looks non-random. I mean, look, there's a whole bunch of zeros right there. But this is all pure Python random number generator. You probably are not gonna break that. At least not in this. Look at this. This looks like a little bit white here. Just random chance. Random things happen. All right. So that's kind of all the simple visualizations we're going to do. There's a lot more you can do with matplotlib. There's a library that comes with it that lets you plot on like a globe or plot on a map of the United States. That is not included with Sage Math Cloud. So that's why I'm not going to go over that. It has some capability for 3D plotting, not as much. And I often find by the time that I'm trying to plot things in 3 dimensions, my brain can't keep up anymore. I have to think very, very carefully. If I can get down to 2 dimensions, I'm much, much safer And if I just plot a whole bunch of those, that'll be more helpful. So next, we're going to get into what's called scikit-learn. And so this is another Python library sort of for classic machine learning. And we say machine learning. The secret is machine learning is a rebranding of statistical modeling. But statistical modeling doesn't sound fun or helpful. It sounds like a painful thing from college or high school. So if you ever did linear regression or ordinary least squares, you've done machine learning. Congratulations, you are already an expert. Scikit-learn just comes with a lot of built-in models to do those kinds of things for you. So tonight we're just going to go over, oh, I didn't want to do that. We're just going to go over linear regression, which is that ordinary least squares, which is saying I need to estimate some kind of number or some kind of decimal number. And we're going to go over what's called logistic regression, which is saying I need to estimate, is this a car or is this a bus or is this a dog? So you're classifying things. Scikit-learn also has things for what's called k-means clustering. We're not going to go into that. That's if you have a bunch of data, but none of it is labeled. So you've got a bunch of, say, pictures of dogs and cars and buses, but none of them are labeled dogs or cars or buses. You just have the pictures. And k-means clustering is a way to do this. Unsupervised learning is what it's called. You sort of look for the features. You say, well, these ones seem to be in this cluster over here. These ones seem to be in this cluster over here. You turn the crank a few times, and out pops what your clusters are. And then you say, aha, that's clearly the dog cluster. That's clearly the bus cluster. Okay. So it's called scikit-learn. It's got a web page. If you search scikit-learn, it's got a great tutorial. It's very nice. But you import it as sklearn. Probably because they didn't want to put a hyphen in their thing. So you should import sklearn, and then you should also do this other line, which will get us some special data sets. And the linear model is what we'll use to do our linear regression. So let's just do that. Import sklearn from sklearn, import data sets and linear model. So sklearn is also nice because it comes pre-built with a lot of standard data sets. So when you're just learning or you're trying things out, they sort of come for free. You don't have to go digging around. Oh, how do I get a data set for that? Half the problem with machine learning is getting data in the right format. And we're kind of glossing over that tonight. But that'll be an issue. That was sort of, you can think of the very beginning of the class was that, where you had an array and you did something. All right. Let's do some linear regression with some data that we're going to make ourselves. So let's make some wide data points. And let's say numpy.arange10, so the numbers 0 through 9. And then let's add random numbers 0 through 9. And our x's are just going to be the indices. Recall when we were plotting, we didn't even think about those. We just plotted our numbers straight away. But here we're going to have to make them ourselves. And let's, yeah, that's good. And we're just going to plot x comma y, like we did before. And then the sklearn part says, hey, do linear model dot linear regression. So what this line does, this just makes a model object for us. We haven't put any data into it. We haven't done anything yet. We just made an object that says, hey, we want to do some linear regression. Get ready for that. And so you store that in this LR for linear regression, or whatever you want to call it. Note the open and close parentheses, but no argument has been provided whatsoever. One cool thing in IPython and in Sage Math Cloud in general, you get tab completion. So if you type linear regret, you can hit tab, and it should autocomplete. If there's multiple options on what it could autocomplete on, when you hit tab, it comes up with a list. And you can say, I want linear regression. And then you can open close parentheses. And Sage Math Cloud, and if you haven't noticed, when you make the open parentheses, it automatically makes the closed for you. If you type close parentheses, that's fine. It will, it won't give you double. but it's something you don't have to do if you don't want to. Okay, so we made our object. Now let's actually fit our linear model to this. I'm not going into the math behind that. There's lots of resources to look into that and lots of different ways to understand it. In this case, I just want to show you the tools of how to do this. So let's do, the command is very common in scikit-flow. It's very general, or not, excuse me, scikit-learn. It's going to be whatever our object was, dot fit, and then we need to pass in our x values. And note, we need to pass that in as 10 rows in one column rather than in this one-dimensional array. It always wants things as sort of two-dimensional, even when it's only one column, notice. So that's something that might trip you up, especially because often you'll have multiple x variables. Here we've only got one. We've just got the index. But you might have some value like this. Let's see. What's something that you might want to predict a number for? Anyone can throw something out here. Housing prices. You've been watching the machine learning course by Andrew Ng. Excellent. That's a good class. So if you want to predict housing prices, some of the variables that you might want are going to be, how big is the house? I don't know. I don't recall who it was.
It's some guy in Central California. He's basically set this work and trying to figure out different ways to bet against death. And, some new vehicles, those new vehicles causing
So I'm not teaching you how to instrument a housing crisis. That is not the goal of tonight. But you might have the house size. You might have, well, what's the front yard size? What's the crime rate in the neighborhood? And those would all be in your big X matrix. In this case, you only have one variable, but that's why it likes it to have it be 2 dimensions. Your Y should pretty much always be one-dimensional for the purposes of linear regression. You're going to put in all these X values, and you want to get out a single Y value. And so that's why we call this reshape. So when you call lr.fit, note we're not saving that off to anything. There's no something equals this. You're just going to run this, and inside this LR object, it will change it. It will compute whatever the weights need to be for our linear regression, because we want to compute some number. And then, given that, you can say, all right, do lr.predict. And oh gosh, what did I do? All right, well, that's fine. I can fix it. You can do lr.predict. And it says, hey, given some x values, not necessarily the ones that we trained the model on. In this case, I happen to have chosen those same ones. But it could be any x's that you have. So maybe you've got some, well, I built this model for housing prices. Now I'm going to look at this new house that was not part of my original data set. I don't know its price. But I know it's 2,000 square feet and the crime rate is 1%. So we're going to do that, and we're going to plot our line on top of our actual data. So we're doing plot.scatter. These are our actual data points, and these are our predicted values. And in this case, because we have some simple data plus some random noise, it should fit pretty well. Not super great. In this case, let me actually change one thing here. Let me see if I can do s equals 1,000. There we go. Now it's a little easier to see those. So these are original data points, and this red line represents the model that we fit through them. And so with linear regression, you get nominally a straight line, but it's a straight line in whatever variables you passed in. So if one of your variables is x and another one is x squared, you're going to end up with something that actually looks nonlinear. And this is an illusion of nonlinearity. And if this is all confusing, you don't have to worry about it. That's okay. Because often when you're doing linear regression, you're going to have too many variables to look at anyway. This is just sort of a contrived example of, well, you've got some data points here, fit a line through them. But again, in a lot of situations, that's what you have. You've got some input x and some output y, and I just want to know, how do I get that line through them? And so if you do this, you can actually get it. Let's see if we can actually get.
So in the plot, right?
Yeah.
So you're plotting x and the predicted values, right?
Correct. The line represents our.
What is the line which is doing the dots?
Right. The dots come from our scatter plot.
From the earlier
Yeah.
one. Okay.
Yeah.
Right.
Our plot is this guy right here.
So x and y values, right? You're plotting.
Yes, you're plotting y values.
So what does LR fit do and what does LR predict do?
So LR fit computes the weights of the linear regression model. When you're doing typical linear regression like this, you can get the weights exactly with a single operation. That goes into linear algebra. Depending on more complex models, you can't get them exactly in one pass, and they'll take more time to compute. Predict says, given those weights and some x value from our data set or not, predict what you think the y value would be. So basically, at some x value, say 3, just give me the y value at this line. So in this case, about 3.
So if you don't fit, if you just predict, like, does it assume that the weights are all even?
If you don't actually fit your model?
Yeah, just
I don't recall how it initializes the weights.
Okay.
They might be initialized to 0. They might be initialized to small random values. For typical linear regression, it doesn't matter what they're initialized to.
Comment probably you'll see right away, right?
Well, right now I fit over it, so I'd have to make a new
Yeah. Okay.
a new instance. We should be able to see if you do LR, if you do some object, a period, and then you hit tab, you get that tab completion, which will tell you what are the things I can do with this object. So for example, I can say I can fit it. I can get just the intercept. There's all this junk that you're not going to know right away what it's doing. But,
Oh. Actually,
so it yells at you.
I think the predict is just getting you the values, right? Whereas LR fit is actually fitting.
Yeah.
Right? Okay.
Yeah. So for example, I want to see what those weights actually are, and I think maybe this lr.coef, this coefficient, does it, underscore. But I don't know. So I'm going to put lr.coef underscore question mark. The question mark in IPython says, give me help about this thing. I want to know what it is. If you run that in Sage Math Cloud, it will pop up this little help for you. If you're in IPython itself, it will be all inline. And so it says, all right, what is this thing you're looking at? This says, oh, this is just an array object. So in this case, coef is not it's not a function or a method. It is the actual array of weights. So I don't even need to type anything.
This is actually giving you, as you said, the weights for the linear equation.
Yes.
The slope and
In this case, I believe, so it's, if you want to have a separate intercept, you need to pass in another variable that's all ones. That's sort of a bias term. That's what an intercept is. In this case, we didn't do that, so we are sort of forcing our model to go through 0.
So is that value 1?
Yes, this should be the slope of the line, which, if you recall, our original data was numbers increasing by 1 every time, plus some random noise. So that's about what we expect. And in fact, if we say there's less random noise, we get a value error. Oh, no. That's not the size of our noise. That's the length of the array. 0.1. If we have 1/10 as much noise, so if you have some array and you multiply it by a scalar, it just multiplies every value in your array by that scalar. So that's a convenient way to do scale things. So now you notice all our points are much, much more on this line, and our resulting slope, we have to rerun this, is much closer to 1, 0.99 something. Whereas, if I had made my noise much bigger, now it's twice as big as originally, our dots are all over the place. Let's see what our coefficient was. 0.82, so not as close anymore. And that's just a function of how noisy is their data, how many data points do you have, how good is your model. All right, get some more water here.
you check this out at all, or are you just doing that? Okay. Okay.
Your cutoff, sorry.
All right, so does everybody have the basic linear model fit? And again, the linear regression is one of the most common tools for predicting a number based on some input, like some decimal value. If your data does weird things, though, for example, if whatever you're outputting is never below 0, that sort of changes the part of your model, and maybe just least squares isn't good enough, depending where you're trying to predict. And there might be other weird situations too. Again, it all depends on the type of data that you're dealing with. Like if you want to predict pizza delivery times, I remember this specific example from one of my stats classes. Pizza delivery times are not going to be less than 0. You're going to have to fit a different kind of distribution to that. I'm not going to get into that tonight, but that's just something to be aware of. That happens to use, it's called a log normal distribution. Often there's ways to like fiddle with your data to get it in the right format, but that's just something to be aware of. But in general, you want to predict a decimal value, least squares is a good first thing to try. And often it'll get you most of the way there. Or it'll at least show you, oh, we're doing something slightly wrong, but it's close. All right, but let's say you don't want to predict a number. Say you want to predict, what kind of flower is this? Is this flower A, or is it flower B, or is it flower C? And we've got a little bit of data, and the data that we happen to have is the petal lengths. I think it's the petal lengths and the petal widths, but they have fancier Latin names that I don't remember. Let's split this cell real quick. So this is just going to make some data, and I want to print this. I like to print things. This comes packaged with scikit-learn. This is a standard data set. It's called, I think this is called the iris set. So there's like 3 types of a certain kind of flower, and they're sort of differentiated by these petal widths. It's like sepal width and sepal length, I think. And so in this case, you can just say, hey, load my data into the x's. So it says all the rows, and we're just going to look at the first 2 features. I think there's a bunch more, but because we want to plot things, I don't want to have too many things to plot. And in this case, our target is going to be y, which is which type of flower it is. And the way that's encoded here, let me actually comment out the x. The way it's encoded is it's either a 0, a 1, or a 2 for whichever flower we're dealing with. And so you could try to use these squares on this. But A, what happens when you encode something that's when your model predicts 1.5? Does that mean it's between 1 and 2? What if it predicts 4.5? Does that mean it's definitely 2? What if, for example, flower type 0 is actually very similar to flower type 2? And you're going to run into a lot of problems trying to predict these things with traditional least squares. But these are what's called categorical variables. And so we need a different model to predict them. And we're going to use a tool called logistic regression. And basically what it does is it's going to build a traditional sort of, you can think of it as like least squares type of model. We're going to have a weight to associate with every feature we have, like that being like the length of the width. We're going to do that for each class. It's going to get its own little score, and then we'll have a way to combine those, compare those scores and say, I'm 50% confident that this is class 1, I'm 30% confident that it's class 0, and I'm 20% confident that it's class 2. And you'll say, looking at those, you say, oh, well, that's probably class 1, because that's the one with the highest probability. So that's typically how these categorical regressions are going to work. You're going to compute a probability of being any given class. And you're going to have a set of weights for each class. All right, so has everybody loaded in the data for this? Once you have, then you can start fitting your model, and you're going to notice it's very, very similar to what we did before. Except this time it's going to be linear model dot logistic regression. The logistic refers to the specific math involved in doing that score computation. You don't have to worry too much about that. You might also hear it just called logit, as in without the S, or multinomial logit. It's all pretty much the same thing. And once you have that model object, we haven't fit anything to it, so if you try to predict, it's going to yell at you, as we found out. You just fit it, just like you did before. And now, behind the scenes, scikit-learn is doing an iterative process to fit the parameters to your model. It's no longer this very nice and clean linear algebra that ordinary least squares did. But you don't have to worry about that. You're just running your model to get some simple classification done. Okay, so you can do that. Let's split there again. This next set, all of this is just to help us make a pretty picture. So you don't have to do that. Or I highly recommend going to the GitHub page and just copying that. This took me a while to retype and several times that I did it. So again, it's github.com. I believe it's ML Workshop. If you go there and load the IPython notebook, this is just going to make a mesh. So we're going to, once we fit our model, I want to essentially predict for every possible combination of our features, x1 and x2, what class would that be? What type of flower would that be? And this H just says, well, how densely do I want to do this? Do I want to take go step by 1 in all my values of my x's? Or in this case, 0.02, so I'm taking a very dense mesh. And in this case, I'm calling them x and y just because we're going to plot them on a single two-dimensional xy graph. But then we'll color each region differently based on what class the model predicts it to be. So this mesh grid thing is it's a NumPy tool. And basically, here we're just building up the grid of all the x's. Here we're building up the grid of all the y's. And here we're just computing what the maximum and minimum values are based on the minimum in our actual features and the maximum in our actual features. Note that this is all the data points with the first feature, and take the minimum, and we're going to subtract a half just to give us a little bit of extra room. This is all the data points on the first feature, the maximum, and we're going to add a half to give ourselves a little bit of extra room. And then given those min and those max, we can pass that to arange, our familiar friend. I didn't tell you, but arange can take a start, a stop, and a step, just like a Python list can when you're iterating through it. But in this case, your step can, of course, be in a fractional value, in this case 0.02. Let's just take a quick, just show you what x is, just so that's clear. No, I'm not taking a break. Okay. And so you can see, in this case, you've got this big grid. You note on every column, you've got the same value, because we're going to have a paired y value with it. And I believe on the y's, every row is going to be the same. Let's see if I'm lying. Yes, and in the y's, every row has the same value. But when you pair those together, that gives you the whole grid that you're dealing with. And it's going up by 0.02 every time. So this is just to make a nice picture. Okay. And then, of course, you have to predict all the values at every point on that grid. This is a NumPy incantation. I really don't want to explain this too much. Basically, we're taking the two-dimensional array, we're flattening it down to one dimension, just to make our prediction a little easier.
How's it do debugging, do you know?
I don't know. I don't know if it does something.
Is it a summing or?
Oh, no. It just literally like unrolls the array. It's pretending it's 2 dimensions, And then it just says, oh no, it's really,
one long array of
yes,
n by n.
of n squared,
Yeah.
n squared things. Yes, that's my understanding. And then we're just going to get the, what class does it think it is based on our model. And so you get this giant one-dimensional array. Well, we have to put that, we want that back in a nice two-dimensional thing because we're going to plot it. So that's what this xx.shape is. So that's, if you call that shape on something, let's do this actually. Let's insert above. So xx was just our mesh on the x's. If you say, give me the shape of that, for any numpy array, you can say, hey, give me the shape. Give me the number of rows and the number of columns. Or your numpy array doesn't just have to be 2 dimensions. It can be 3, 4, 5, 10, 100 dimensions, however many you want. And it will give you a tuple with all those dimensions. If you have more than 2 dimensions, it's going to be hard to plot and understand what's going on. But depending on your problem, it might make sense to do that. Because, well, maybe I've got a box, and inside this box, I've got a grid. And then I've got box number 2, and I've got another grid inside of that, and box number 3. And maybe all these boxes are in warehouse number 1, and warehouse number 1 is on street number 7. So it can often happen that you have many, many dimensions. You should be careful making things with lots of dimensions and big dimension sizes, because you might eat up all the memory in your machine. So things to be aware of. If you're using NumPy and you're not careful, there's a chance you will crash your Python session, which is not the end of the world. You can just reboot it and reload things in and try to be careful. This is something I do, I don't want to say on a routine basis, but it does happen. And that's not necessarily that NumPy is unstable. It gives you a little more power and lets you shoot yourself in the foot sometimes. Okay, so after you reshape, you do z.reshape of just our mesh. We're going to make a new figure. Often we've been doing this, we've just sort of been relying that we're in the same cell whenever we're plotting. This says definitely make a new figure. Whatever you're doing, whatever you had before, make a new one. And so we're going to plot into a new plot. And if you've made your numpy.mesh the way we did above, like this, you can say plot.pcolorMesh. And if you recall earlier, pcolor is just a heap plot. Mesh says, well, do the things at all these points. So at the x, at this x and this y value, plot this z. And what we're doing here, I want them to color them based on the color map of paired. So whatever things have the same color, I want those to have the same value. And we're going to see what that looks like in a second. Some of you have probably already done that. And that, again, that's all just a plot in the background. What are the colors of this thing? But really what we want to do, we want to plot our stupid training points. What did we train on? How well did we do on our training data? And so we can just plot a regular scatter plot. Our x's. In this case, we want to plot x1 versus x2. But we want our colors to be whatever the label was. And so that's something you can do. You can pass in this array or list as your colors, C. In this case, I'm saying make the edge colors black so they're easier to see. Make them all size 100. Make the line width on the edge color 2 so it's a little easier to see. And again, we're doing the color map is paired. So these should be the same colors as these guys, as our color mesh. And that's because the predictions are the same. Note that we're predicting in our color mesh here, it's giving us a single class color mesh. You can get the actual probabilities out. In this case, it's just giving you whichever one has the highest probability. And also, you can relabel axes on your graph. You can say, hey, I want this to say sepal length, and I want this other one to say sepal width. And those are the special names of these features. But those can be whatever. So if you're making a figure for an academic paper or just to show someone else, to show the boss, it can look reasonably pretty. That's what these things are too. Xlim says, hey, only show me things from this point in the axis to this point in the axis. So from maybe this is 0 up to 10, or maybe it's -5 up to 100, and likewise for the y's. And the x ticks, that's to relabel the actual tick marks. So where before, you might recall, it said like 0, 2, 4, 6, whatever. If you relabel it with nothing, you're just wiping out the x's. But you can pass whatever you want in there. So if you had different categorical labels, you could do that. Well, let me try to run this and see if it works. It sometimes takes a long time. Okay, it worked. And here it's super hard to see the brown from the red, but you can see we've got all these blue points over here, and this background blue means that's what the model is predicting. It's predicting this is class blue, whatever that is, in this region, class red in this region, and class brown in this big region. And you can see it's done a pretty good job on the blues. There's one blue that it got wrong. The reds and the browns, it's kind of hard to see. I'm going to go back up to the code, actually. I think it might not be 100% deterministic because it's this iterative process for the logistic regression. But you're probably to within an error term, you're going to get the same values out.
For the same input, we will get the same results.
Yeah, there's going to be a random seed that determines exactly what those little error terms are. But I don't, if changing the random seed changes your model significantly, your model is probably wrong, and it probably needs some work. So let's just see. You got nice pictures. I'm not sure if you can see the brown and red. So you can see the blue is clearly very different from the brown and red, so it's not surprising that the model did a better job predicting those backgrounds. All right. How are they going over here? Peter troubles? Right, down to 1 second. You ready to go over there? Okay. You got it, Star?
I'm actually just watching this one.
Okay, that's fine too.
Yeah. It went past my time ability and my squinting ability.
I apologize.
It's okay.
I will be gathering feedback from people at the end. All right, so that was all just to do some logistic regression, and we got a model that did okay, so that's interesting. But let's talk about something a little more interesting. One quick aside. We've been using this library scikit-learn. There's lots of other libraries for data analysis. One popular one you might hear of is called pandas. I'm not going to go into it tonight, but it tries to be a lot like a statistical computing language called R. It's really annoying to search for things in R because it's just called R. But pandas tries to be very like it. It makes it very easy to manipulate data sets if everything is nicely labeled. For example, the housing prices, you can just pull out a single feature and do lots of other things very conveniently. So if you want to check out more, I would recommend looking at pandas, and they also have a good tutorial. They are not necessarily interchangeable. Yeah, they do. They can do similar things. Pandas, I'd say, focuses more on manipulating your data. Scikit-learn focuses more on modeling your data. I don't know how able scikit-learn is able to take data directly from pandas. Pandas uses what's called data frames, so they're not just arrays anymore. So I don't know how well. It might be fine. It might not. That's something to explore. All right. Now we're going to get to the final section. We're going to build a neural network. So if you've been on the internet and you've seen the pictures of Google's deep dreams, those are all based on neural networks. And these are things that let you do truly nonlinear computations. Consequently, they're a lot harder to train, and they're a bit more of a pain to specify. Thankfully, Google has come out with a library called TensorFlow that will do a lot of this for you. And so if you just import TensorFlow as TF to save yourself typing later, and if that doesn't work, let me know. It should. And it shouldn't return anything. It should just not yell at you. All right. And skflow is how we're going to use TensorFlow. So that's just a nice library into that. This is some stuff that you can read later if you want. You can like classify images of handwritten digits. That's a classic problem that the Postal Service was very interested in. We're going to use it to do the same problem we did with logistic regression. We're going to classify flowers, and we're going to see how we get different results. All right, so let's import skflow, and very similar to what we did for scikit-learn, or excuse me, I'm actually re-importing some sklearn stuff. So import skflow, and then we're going to, from sklearn, we need to import a couple more things. We don't actually need to re-import data sets, but I forgot to take that out. Cross-validation is going to be how we check our data. And metrics, do I actually use metrics? Import metrics anyway. We'll see if I need to use that later. Okay. And now, in one line, you're going to build a neural network. And the way you do this is a lot like you do in scikit-learn. You're going to say skflow.tensorflow DNN. DNN stands for deep neural network. The deep refers to how many layers, and I don't actually talk about what a neural net is here. All right, I will open up a second. We're going to go over what a neural net is in just a second, actually. Is that in this one? So I get for having multiple versions of things. No, I don't talk about it at all. All right, never mind. So what a neural net is, I'll just try to explain it verbally, which is the worst way to explain it. You've got your original features, in this case, your sepal length and your sepal width. You want to send those. In logistic regression, what you do is you compute some weights for each class, and that gives you some probabilities for each class. In a neural network, you're going to compute some weights for a bunch of nodes that are kind of arbitrary, and then you'll put that through another function. And now you sort of have some new outputs, and maybe then you'll put those new features that you've computed into some weights to get your classes. That would have one layer of nodes. And you could have 10, 20, 100, a whole bunch of nodes. So now you've sort of got a set of weights for each node for each of your features. If you just have one layer, that's not called deep, but that is a neural net. You can say, well, give me that one layer of nodes where I'm computing a bunch of features, and instead of having that feed directly into my output classes that I want to compute, have it feed into another layer of nodes, and then another layer of nodes, and however many layers of nodes, each time computing new weights. And then eventually you get to the end and you have to compute your classes. And the catch you're probably wondering is, how the hell do you get all those weights? So before, with linear regression, you compute directly with linear algebra. With logistic regression, it's a pretty quick optimization process that's iterative called gradient descent, or it might be called stochastic gradient descent, or there's probably dozens of other ways to do it that's relatively similar. It turns out, in a neural net, you can use the same gradient descent method, or stochastic gradient descent method. And I'm not going into it here, but it's how those nodes actually transform the weights and values coming into them is what determines how easy or painful it is to do that gradient descent. And so what essentially you're going to do is you're going to put your data in, you're going to initialize it to a random set of weights initially. You'll put your features in, you'll get some prediction for what the class should be, and that's called the forward propagation. And then your model will say, well, how wrong was I? Let me look at the actual prediction for that class, and you back propagate that error. And that actually gets into calculus of a certain level, but to actually use it, you don't really have to know the calculus to do it. Just know that you're back propagating the error. And TensorFlow is pretty nice. You can have sort of an arbitrary, it's called activation, how these nodes handle their input, and it will automatically compute the derivative for you. And in skflow especially, it makes it really easy to just specify a neural net. And so that's what we're doing here.
And the deep view of the multiple layers is how brain recognizes multiple layers, right?
Yeah, so the reason you might have multiple layers is you can think of each layer as computing certain features. And you might have these nodes together happen to be computing some feature. These nodes happen to be computing some other feature. And if those two new features go into the next layer of nodes, it's like you've got a whole new model. It's like, oh, I've got two new features coming in. To me, those mean something together. It creates yet another feature.
One most granular, then probably then the boxes, then the houses, and that.
Yeah, and it depends. You can specify different kinds of neural nets. So this is a deep neural net. We're using this to classify things. You can use neural nets to do lots of different things. We're just doing traditional classification. And in this case, this particular program, it has what's called densely or fully connected layers. So every node in a layer will feed into every node in the next layer. So this creates a whole lot of parameters, and it can get out of control very quickly, which is why a lot of neural net libraries also use GPUs, your graphics processing units, to do the computations. But we're on Sage Math Cloud with the free account, so we won't be doing that much. So use this deep neural net classifier. The hidden units. This is how many nodes do you want on each layer. I'm not going to go into how do you figure out how to do that. I just want to show you that they make it dead simple in skFlow. You give it a Python list. You say, well, I want 10 nodes in the first layer, maybe 20 in the next layer, maybe 10 in the next. I just kind of picked these semi-arbitrarily. You have to say, how many classes do I have at the end? We've got 3 different kinds of flowers. And steps equals 200, I've actually not figured out what that does. So if someone figures that out tonight, that would be great. I tried looking at the help, and it was not very helpful. Note that just like before in scikit-learn, we haven't actually passed any data in yet. We've just specified, this is what I want my model to be. This is what I want the neural network to be like. If it's got this set of units, and it's got to have this many outputs, and whatever the step size is. And then, just like scikit-learn, you can fit it the same way. You say, I've got my features, and I've got my labels. And it'll show you this iterative process. The epoch, that's how many times it walks through your data. So what it's going to do when it does its gradient descent, it'll look at, say, 10 or so data points at a time. It'll compute the errors for all of them with a single set of weights, and then it'll fix up the weights, rather than after every single data point computing the weights. You can often save a lot of time this way. And the epoch is how many times you go through all of your data. So let's just run this. You just keep adding more. Let's add another layer. I don't know how bad this is going to be. We just add another layer. Boom. This loss is sort of an internal cost function that it's using to do the optimization. If this is not going down, then your model is not working. Yeah. Huh? It might be worse than the other one.
Steps is usually to converge faster.
Is it? Okay.
Yeah,
Interesting. So, but the loss from one model might not be comparable to the loss to the next because we've got so many more features. Let's suppose we've got 3 layers. You can feel free to add more or fewer layers as you're playing around. Experimentation is encouraged. That's a nice thing about the IPython notebook and the Jupyter notebook. They make it easy to just try something and see if it works. All right, and it spits out this, oh, I made a TensorFlow classifier object, and you can see all the parameters it actually set at default. So batch size is how many data points it looks at in a single pass before it updates the weights. What would I do? Continue training, I believe that says when I add new data points, like if I were to call skf.fit again, continue training equals false means compute all new weights. If I said true, I'd sort of be updating the weights each time. And of course, we got our hidden units, learning rates. You can try to crank this up, and it might make your model converge faster. However, if you make it too high, you will often cause your model to not converge at all. You will sort of overshoot your optimization. The optimizer, SGD, stands for stochastic gradient descent, and stochastic is just another word for randomized. So if it's not exact gradient descent, it will perturb itself a little bit. In TensorFlow, the default random seed is 42, so if you like Hitchhiker's Guide to the Galaxy, you'll enjoy that. And we're saying verbose equals 1 because that means it's giving us all this output. And again, you can just say skf.fit. Is that going to work? You can ask for help, and you'll say builds a neural network and model given the provided model function. So this is sort of a generic input. Our model function is this TensorFlow DNN, and it'll tell you what all kinds of things that it's expecting and what it'll give you in the end. All right. So really, we want to see how we did though. So this is a good time to copy that code from up above that you used to plot the mesh. And we're just going to change it up a little bit. We've got the same XX and YY values, right? It's the same mesh that we want. But instead of using our logistic regression classifier, we're going to use the skFlow classifier, the neural net. And you're going to predict it the same way. And you got to reshape it the same way. And again, this is just to forcibly plot a new figure. This is going to give us the colors in the background of our image that tell us what class the model thinks this particular point should be. And then we're going to plot our actual input data points, so we'll see how we did. We're going to fix up our axes a little bit. We're going to limit our axes to only values we're interested in. And we're going to get rid of numbers that are just kind of going to, that maybe you would actually want to know that a certain width would give you something. But for just the purposes of seeing how the model did, we don't actually care. So let's see how this goes. Alright, it yelled at us. That's gotten normal. We've gotten used to getting yelled at. And so depending on what you did to your model, if you changed something, you might see a different image. But what I really want to point out here is that in this particular instance, you've got a definite nonlinear shape going on here. It's no longer just a set of intersecting lines defining the boundaries. You've got something slightly different. And so maybe this area, where's the mouse cursor? This area over here is pretty good at getting brown. This is mostly red with some brown, and our blue is still pretty good. So let me go back up to the code in case anyone's still copying that. And has everybody trained their first neural network? It is now a deep learning expert. Did anybody find a much better model for this data? Right, in this case, like sort of the point is that these two features are not really enough to distinguish between, right?
So somebody asked, like, if you get a ground
If your model's pretty brown, you can say that's probably actually brown.
if your model is
If your model's red, you're kind of thinking, well, it's probably red. Yeah. Or you can add more features. You only get the first two. Well, let's go over here. Here's an island. So that is the last official thing that I have. And so I want to open it up to you guys. If anybody has any questions, or I encourage you to play around with any of the models, the linear regression, the neural nets, you just move around with that. That's a really great way to work. If you have a particular project at work or so, that's a good way to figure out what's going on. Here